It's just dumb. Okay. Okay, that'll have to do then. All right. Which I have actually 3 on 3 different things.
Okay.
One of them is on resistors. Well, 2, I guess. One of them was similar to the thing that we went over last time, so I'm not going to redo that. It's just a different problem on the same concept. So concepts are the important part, not the problems. I have 1 on capacitors and 1 on magnetism. How's magnetism going?
So I mean, okay. So I was doing magnetism homework with Sebastian, who basically like told me how to do it if I didn't know how to do it.
Okay.
So it doesn't count. And okay. Right. This one. Okay. Yeah. This one doesn't work. But yeah, I get it.
You want to use this?
I just didn't do one question. It's RS loop circuit 2.
I only did 1 on magnetism. Yeah, the other one is on capacitors and the other one's on resistors. I can do that.
I mean, RS circuits have capacitors, so we can do it.
RC?
Yeah. Yeah, I didn't.
Which is RC circuit? Yeah.
I didn't do this one.
Oh, you didn't do the RC circuit one. Okay.
Yeah. Okay, because I didn't find this one. I don't know how to. I know how to do the other ones, but the other ones need this one, and I'm stuck with that one.
What is Q infinity? The charging the capacitor after the switch has been closed for a very long time.
Yeah.
Okay. How did you think about it? How did you try to find the charge?
Okay, but like there's a formula.
Whichever formulas.
Formulas, when you understand what you're trying to find, then you can use formula. Just focus on how are you trying to find this. What situation? So Q infinity.
Yeah.
Infinity, so after a long time what? Of the circuit being closed, right?
Yeah.
Okay, what happens?
So after this closes, the current runs, and this charges a lot, then it stops, and the current goes back from like this way.
Right, but it's still closed right now.
It's still closed, yeah. Yeah, and then it's asked to the charge. So it's like on maximum.
Right, so C is charged maximum, right?
Yeah.
Okay, so where is the current flowing in the circuit?
Here.
Is there current flowing there in the circuit?
What do you mean?
Is there current flowing here?
Oh no, not here, on this one.
On this one, on the right?
Because
in
this
which
is
direction?
closed. If it was going this way, then now it goes this way.
But no, you still have your switch closed. Switch is still closed.
Okay.
Right? First it was open like this, right?
Mm-hmm.
Then they closed it.
Yeah.
Okay. After a long time, after they close it, then they waited a long time. After a long time, they're asking you about this charge. You have to reopen the switch.
Oh, okay.
Yeah. Switch is still
So
closed.
it's still that way.
So current is still flowing from the battery, right? Because the battery is on short circuit.
Mm-hmm.
Current is still flowing this direction.
Mm-hmm.
But after a long time, the capacitor is going to be charged,
Mm-hmm.
right? So the capacitor is charged. What's going to happen? What happens to the current through the capacitor
Change direction.
when it's completely charged?
Mm-hmm. Yeah.
No current is going to flow through it anymore.
Oh, okay. Yeah.
So
Oh, before the switch
before
is
it's open,
open.
yeah. You
Okay.
haven't opened
Yes.
the switch
No
yet.
current. Okay.
Everything's closed yet.
Mm-hmm.
Sorry, everything's still closed. You haven't opened it yet. So you don't have current flowing through your capacitor.
Okay.
The only current that is flowing is
From
this
battery.
branch. Yeah, from the battery
Okay.
in this branch. Because the capacitor is not letting current flow
Oh.
through it.
That's why we just need to consider resistance 1, 3, and 4,
Yes.
and not 2.
Not to.
Okay. 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 That was my question.
Okay.
Okay, thanks.
Do you know how to do it now?
Yeah.
Okay.
I can do it later. Thanks.
Right. I'll do one on RLC first then. Did you have magnetism as homework this week?
Mm-hmm.
Yeah? How did that go?
Yeah. So that's the one I told. I was doing the dispatching, and whenever I couldn't do something, he just would tell me how to do it. So. It didn't count. Like I finished it on my own.
Right, we're first do a capacitor problem.
Okay.
Try to make it neat this time. To 12 volts. And this is our switch.
So is this like RC circuit?
Yeah, it's an RC circuit.
So you have R1.
So I'm just going to add a little thing here.
Okay.
Yes, the capacitor is filled with a dielectric. Those are four. Okay?
Mm-hmm.
Okay. Problem says, at first you have the circuit. Okay, nothing's happening. Capacitor is completely uncharged. At time t equals 0, for example, at t equals 0, switch is closed. And after a long time from that, this capacitor is removed. So first of all, at t equals 0, we close the switch. Then, after a long time, this capacitor is removed. Okay? The dielectric, after the capacitor is removed, the dielectric inside the capacitor is removed. Then the capacitor is going to be put back into the circuit without that.
Okay.
Look, it's just different concept. It's a concept of dielectric, concept of charge, and the concept of RC circuits, all in one problem. It's not a problem. It's just three concept problems.
Okay.
Instead of one concept on each problem. So, okay. First of all.
Okay, let's start from like.
Okay, first of all, we close the circuit, right? What happens?
Okay, so when we close the circuit, current starts running. And I have a question. When the capacitor is filled with dielectric, how does it act? Okay, so.
What does the dielectric do to the capacitor?
I know it increases capacitance.
It increases capacitance, okay. So, originally it would be equal to Q over V, right? Q equals CV, C equals Q over V, right?
Mm-hmm.
Then or C over V.
Okay. So when the switch is closed.
When the switch is closed.
Current starts going in this one.
Current starts going.
Yep.
In where? In this one?
Mm-hmm.
Yes, okay.
And, yep.
Okay. After a long time.
After a long time, the capacitor will be charged.
The capacitor is going to be completely charged.
And it has dielectric in it.
It has dielectric in it.
Okay, and then the current will stop going.
Now we're going to remove the capacitor. Since when we remove the capacitor from a circuit, the only thing that stays the same is the charge, right? Remember when you have it, the dielectric is still going to be there. We're first going to remove the capacitor before we remove the dielectric, right? We're removing the capacitor. Now, remember that when we remove a capacitor, right, the only thing that stays the same, no matter how we manipulate the
is charge.
Is charge. No matter how much. So if we make the plates bigger, if we increase the distance between them, put a dielectric, remove that, the only thing that stays the same is charge. So that's why charge is a useful quantity to have when you're manipulating a capacitor outside the circuit, right? So the first thing you want to do is find the charge at t equals infinity.
Okay.
Because they're saying after a long time. Actually, let me just write down the problem.
Okay, so
At t equals 0, switch is closed. At t equals infinity, C is removed, and then dielectric is removed.
So what you want me to do is to find the charge.
We want to find the entire problem is we want to find currents I1 and I2. The initial values, initially after the capacitor has been restored in the circuit after removing the dielectric. So you understand what's happening, right? Closing the switch, charging this to the maximum, taking the capacitor out, taking the dielectric out, putting the capacitor back in.
And what's the current?
What's the current I1 and I2?
Okay.
We're also going to consider two cases. If we put the capacitor in while this switch is open, and if we put the capacitor in while the switch is closed. Okay? So in both cases, we're going to have to find Q infinity, which is the charge after a very long time on the capacitor. Okay? So, on this capacitor.
So we know Q is C divided by V. But we don't.
Yeah.
What?
We know Q is equal to this is the equation for Q, right?
Yeah. Okay. Now we have to find V.
We have to find V after a long time. Okay. What's the voltage across the capacitor after a very long time?
Yeah, that's a problem.
Why is that a problem?
Is it still 12?
Why is it 12? Why do you think it's 12?
Because it's a cross.
What about this resistor though?
Okay, but there's the second one as well.
Yeah, there's a second one. There's two resistors. So there's two voltage drops. Okay? When you connect the circuit, so after a long time, the current is zero. Yes.
So the voltage there will be the same as voltage as R2.
Yes, the voltage of the capacitor is going to be the same as voltage of R2 because they're connected in parallel. Okay. So how do we find the voltage of R2?
We can write Kirchhoff's rule.
We can write Kirchhoff's law, right? So we can either do that or we can just use Ohm's law directly because these two are in series, right?
Okay.
Yeah.
So R1 plus R2.
R1 plus R2 is equal to 8 plus 4, which is equal to 12. Okay. And I1 in this case,
It's the same.
I1 is equal to 12, which is the battery, over 12, which is the resistance, right? Which is equal to 1 amps.
Okay.
Now to find the voltage across this resistor, just apply Ohm's law again.
Divide V equals IR, so it's 1 times.
1 times.
R2 is 4, right?
Yes.
4.
Times 4, which is equal to 4.
Okay. 4 volts. And it will
This
be
is
the
the
same.
C. Right? That's the voltage of your capacitor. That's the voltage of your capacitor.
Okay.
Now, you want to find?
We can find charge now because
We can find charge, right? Okay. How do we find charge?
we know the capacitance with dielectric.
Okay.
And we know the voltage, so we can just.
So
do we have to from microfarads go to farads?
you don't have to as long as we move that. So
Okay.
so this is your Q is going to be microcoulombs, right?
So it's just going to be 4 times 6 divided.
Okay. So Q is going to be 4 times 6 divided by
Divided by 4 we found.
divided by the voltage, which is 4, which is equal to 6 microcoulombs, right? Because the thing was in micros, so we still have to move that over.
Okay.
Microcoulombs. Now we remove the capacitor.
Mm-hmm.
We remove the capacitor,
Okay.
and then remove the dielectric, right? Okay. So we took the capacitor out. Now the capacitor is outside. I'm going to redraw it here. The capacitor has a capacitance of, this is, let's call it C before. Well, yeah, I guess. Let me do that. C before is equal to, see, we're assuming here, I mean, it doesn't really matter, but assuming we did this assuming that C is 6 microfarads without a dielectric. Okay, just that, because if we assume that it was a dielectric, then we would be already taking into account this. So we're assuming that this is without dielectric. Okay. So C before was 6. 4 was it? Was it 6? Oh yeah, 6. 6 microfarads. Right. Now C after is going to be equal to
dielectric, you mean?
Now, when we remove the dielectric. So this is 4. Right?
Hold on, it was not 6 then.
It was actually 6 here.
Wait.
6 times 4.
6 times 4, yeah.
24, right?
Yeah, so it was 24.
24. Now, our new one has no dielectric.
It's 6.
Has 6, right?
Okay.
So C before, sorry, right? 24 microfarads. C after has 6 microfarads, right?
Yeah.
Okay. And now what do we want to do? We're putting the capacitor back in. So we're removing the dielectric. We're putting the capacitor back in. And we want to find I1 and I2.
So we will put the capacitor without the electric. So it just will be 6 microfarads.
So the capacitor is going to be equal to 6 microfarads. But the charge on it's not going to change, right?
Uh-huh.
The only thing that does change is
Oh, so we can find voltage.
we can find the voltage. If we find the voltage, we know how much voltage the capacitor has when you put it back in, which means you can compare the voltages and find currents.
Okay.
Okay. So now Q. Sorry.
We know
Q.
Q.
Yeah, we need Q. Q equals CV. So V is equal to Q over C, right?
Mm-hmm.
So V
And it's going to be 6 over 6.
is equal to the charge, sorry, over 6 is equal to 1 volts.
Yeah, okay.
Is that right?
Yeah, because we were dividing microcoulombs by microfarads. Okay. Yeah?
It should be right. Yeah. B is equal to Q over C. When we remove the dielectric, we're basically multiplying by 1 over 4. We're multiplying by 1 over 4.
What do you not like?
I think I wrote this problem differently. Because no, the thing is, I wanted the voltage to be higher when we put it back in. But that's fine, I guess.
Why did you want it to
That
be
wanted to work.
multiplied?
Just something different, I guess. I think when I wrote this problem, I took C microfarads to be inside that. Would that make sense? C times 4 is what I think is going to be. Over 4.
So you wanted 6 to be with dielectric?
Yeah, that's fine. Never mind. Let's just do this. 1 volts. Okay?
Okay.
Voltage across the capacitor. Voltage
So
across the
voltage
capacitor.
of R2 will be also 1.
So the voltage across R2 is going to also be 1, right?
Mm-hmm.
So, okay, let's consider 2 cases first. First, now we're putting that capacitor that has 1 volt across it.
Okay.
We're putting it back into the circuit. When first we want to put it back in when the switch is closed, and then we want to put it back in when the switch is open.
Okay.
Oh. Why did we do that?
No, wait.
Q is equal to CD. Yeah? Did I just mess that up? Ooh.
Q equals
This
CD.
is why. That's why it should be Q is equal to CD.
I'm bad at formulas, so I just look them up.
No, I'm also forgetful. The only one I remember from these is Q is equal to CD, and I have to drive it every single time, and I make mistakes deriving it. That's why yeah. Okay. Q,
Okay, it doesn't matter. So
okay. Q is equal to CV, so Q is equal to C4, which is 24, times V before, which is 4.
Okay.
4 times 24 is 48, 96.
Okay.
Right?
Yeah.
48, 96, yeah. So this one is right, thankfully. Which is equal, so V new after removing the dielectric, the new capacitance is going to be 6. So that's going to be 96 over 6. Okay, that looks nicer.
96 over 6. What's 96 over 6? 16. Okay. So we have 16 volts. Okay, that's my number. We have 16 volts running across the new capacitor. Now we're going to take two cases. The first case that we're going to take is the switch is closed, and the second case is the switch is open. Now, if the switch is closed, I'm going to just draw this thing. So this is switch is closed. Battery 8 ohms. This is 4 ohms, and this is your capacitors. We only want the initial voltage. You don't have to worry about things over time. I1. This is couples. This is I2. This is I1, and this is your capacitor, which now has 16 volts, right?
Okay.
16 volts plus minus.
Oh, okay.
What's I2?
It's just okay. V equals IR. I equals V divided. It's 4.
Right. 2 is equal to V2 over that one plus 16 over which is 4. What's I1?
Okay, it would just be like 12 minus I1 times 8, and then minus 16.
Yeah, you can do that. You can do that, yes. 0? Oh, it's not going to be 0. But I mean, you can do Kirchhoff's law. You can do Kirchhoff's law.
I do that because I understand it.
Okay, so look.
Okay.
What did you do here? When I asked you through it, you looked at the voltage across it, right?
Yeah.
And then divided by the resistance, right?
Mm-hmm.
What's the voltage across this one?
Oh, it's just 12 minus
16
voltage.
minus 12.
Yeah.
16 minus 12 over 8. That's going to be if the current is going in that direction.
Yeah.
Right? Or if you said 12, since we want the current in that direction, we would take, assuming this is the higher voltage, 12 minus 16. 12 minus 16 divided by the resistance of it, which is 8.
Okay.
Right? 2.
Okay.
Which means that negative means the current is going in that direction.
Mm-hmm.
Right? Okay. Now we take case 2. All the three switches
open.
when the switch is open. Oops. Now if we put it back when the switch is open, still this is 16 volts.
Yeah.
Okay.
But didn't you say that if we open this one?
Where?
In the first one. But
In this one?
Yeah.
Okay. That means I was 0.
Okay.
I want there. Since there's no current here, I want to equal to 0.
Yeah, and we will calculate I2 just 4. Okay. That was fun.
It was, wasn't it? Okay, I'm just going to move on to a new page now. See, pretty easy, isn't it? No, really. It just seems complicated. But this one is on magnetism.
Mm-hmm.
Do you want to go over magnetism things first? I mean,
No,
do
it's fine.
you not understand? Do you understand everything in magnetism? Do you know how to?
I mean, okay, there's only right-hand rule that we went over.
Yeah.
And there's one formula we used, Q times V equals MV over R. That's the only thing we did.
Times energy over R.
Mm-hmm.
Yeah, because F magnetic force.
Oh,
is
and it
equal
would
to
be
QV.
V times sine or
Sine
cosine.
yeah,
things.
sine. Because it is actually F B Q times V cross.
Okay.
V, right?
Okay.
Cross. V cross B is data. Okay. All right. Q is charge. V is velocity.
Mm-hmm.
So it's going to be V cross B. So V cross B gives you the direction of the magnetic force, right?
Okay.
And which right hand rule you prefer? Which one do you use?
What do you mean?
I mean, which right-hand rule do you prefer? There are multiple ones. There are multiple ones that you use.
Well, just the ones. Okay, so if there a dot, okay, if you see a line like this, then you like this, then it means it goes that way.
And then, okay.
Like, okay, if there are X's that comes to your rule, then you put here, turn, and it goes that way.
That works.
Well, I'm left-handed, so I'm bad at writing. I like when it's like electron, so you use left-hand.
Left-hand rule.
Yeah.
Just use left-hand rule and take the opposite of that if you want. Yeah, the one I prefer is B, the direction of the thumb. B is in the direction of this finger, and the one that this finger points at is the force.
How do you use this?
Q.
What is Q?
Sorry, B. This is B, which is so if A cross B gives you C, just like B cross B gives you F.
Mm-hmm.
It would be A cross B, perpendicular to it, gives you F or C.
How do you use it on the picture?
Okay, so let's have a.
Okay.
This means coming out of the page,
Yeah,
right?
it points at you.
Pointing inward, sorry.
Okay.
If you mix these up, the way to think about them is think about a screw.
Of what?
A screw.
What is it?
So, a screw, one of these things. I don't know how to draw screws.
Oh, okay, that you put it on the wall too. Okay.
The one you turn, right?
Okay.
If you look at the screw in this direction, it's going to be pointing inward.
Okay.
Right? If you look at it in the other direction, you're just
Let's see a dot.
Okay.
For the screw.
right. So if you have a particle moving at a speed v like this, a charged particle moving in this direction, we have v, right?
Okay.
Cross b, which is inward because it's going into.
Oh, so it's gonna go that way.
It's going to go in that direction, yeah.
Oh,
So it's
okay.
going to turn like this.
Okay. Alright, and yeah, basically that's it. It just tells you the forces. Goes in that direction. Q is equal to mv because centripetal force is that. So what we're going to do is something similar to it, not exactly. I mean, based on it, but also using a concept from previously. The best way to keep things in your brain is to review them every now and then. So we have a charged particle here, Q, positively charged particle, right? It is about to go at a velocity of v is equal to 2 meters per second, right? It's entering at a velocity of 2 meters per second. You have two infinitely charged plates, okay? Two infinitely charged plates. One has a sigma of 70.8. Let me just write that.
Two infinitely charged plates. One has a charge of positive 70.8 sigma, and the other has negative.
What was sigma? Was
Surface.
Surface charges.
Oh, surface.
Okay. Now it's going to go inside between these two plates.
Mm-hmm.
And we're assuming that the mass is approximately 0. We're going to forget about gravity. We don't want to deal with that, assuming mass is negligible. Now, this positively charged particle is going to start moving in a direction parallel to these plates, okay?
Mm-hmm.
Parallel to these plates. And what's going to happen when it starts moving in this direction? It's a positively charged particle, and it's in between two plates, right? Which means you have an electric field.
Oh, yeah, plus and plus don't
Plus
like
here,
each
minus
other.
here, plus don't like each other.
So
They're going
plus
to help
will
each
go
other.
that way.
So it's going to start to turn in that direction, right?
Mm-hmm.
Now, what we want to do is add a magnetic field to make it move
in a straight direction.
Oh, okay. Sure.
There was something similar to it, I think, in the reflectors.
Not exactly magnetic field, but there's that device they use for speeds for taking, I forgot what it's called, but
There was something kind of like that. But anyway, we want to add a magnetic field inside here to make this charge move in a direction, keep moving in this direction.
Okay.
Right. What do you do? For it to move in the same direction, right? Now you have, first thing you have here is because this plate is positively charged, this plate is negatively charged, right? As you said, it's going to be affected, once it enters here, it's going to be affected by an electric force, right?
Okay.
Due to the electric. So let's call this F electric.
Okay.
For it to move in a straight line, we want to balance out that force with another force, with a magnetic force. Okay? So we want to add a magnetic field so that it affects this charge with a magnetic force pointing in that direction.
Yeah.
Perpendicular. Completely opposite of this one. And its magnitude has to be the same thing so they can cancel out and the charge continues to move in a straight direction. Okay? So this is F of E, which is electric force.
Yeah.
It has to be, magnitude of this has to be equal to the magnitude of the magnetic force.
Okay.
V has to be equal to F of B for this to work. Now what's the force going to be on this charge as it moves through these plates?
We can calculate it.
Yeah, how we calculate it.
What was the force?
What was the force? Okay, we know how to find the electric field, right?
Yeah.
What's the electric field? Electric field of two plates. Okay, of one plate is going to be, so if the charge is here, right, positive charge is here, it's going to be affected by one force due to, like one, so at a point here, you're going to have an electric field coming from this plate, in this direction, right? Its value is sigma over 2 epsilon naught.
Okay,
Right?
yeah. Exactly.
And there's another one from this one going in the same direction, so plus sigma over 2.
Okay.
Sigmas are the same value, so you're just going to have sigma over epsilon naught.
Okay.
Okay, electric field. Okay? And remember that, how do you relate electric field to electric force?
Oh, forces. Oh my god, there are a bunch of rules. Whatever, force.
Remember that force was,
KQ.
remember force for a point charge and point charge was KQ over R squared. R squared.
Yeah.
When we went to electric field,
It's just KQ.
KQ over R squared. What happened? We just divided by Q, right?
Yeah.
That means F divided by Q gives you E,
Right.
right?
Exactly.
Because to get rid of this, we just divide by Q. So that when we want F from E, we just say the electric field times Q gives you F of E, equal to the magnetic field. What's the magnetic field? The magnetic force, sorry.
Oh, yeah. B times.
Q times V times V, right?
Yeah.
Q, V, E. So we're only looking at
And the charge is the same.
Charges are the same. Yes. Notice that the question does not give you charge, right?
Oh, yeah.
At first glance, you think they give you
Yeah.
charge.
Okay.
Okay.
And then E is
E is equal to
sigma, whatever.
sigma over epsilon naught.
Okay.
Okay, so that means sigma over epsilon naught is equal to VB.
How do we find B?
B,
Yeah.
we know sigma.
Right. Okay.
We know B.
Yeah. Sure.
B is equal to sigma over epsilon naught.
Okay. That's
Okay.
not that bad.
It's not that bad. Sigma was 70.8. Epsilon naught is 8.85. Oops. Times 10 to the negative 12. This is times 10 to the negative 6. Times
2.
V was 2. And this gives you times 10 to the 6.
Okay.
Tesla.
Oh wow, that's a lot.
I just write these problems so that the numbers would work out. So.
Okay.
Okay. That's 4 times 10 to the 6. That's okay.
Yeah, that's it. Is that the like? Is it the answer?
That's the magnitude.
Yeah.
What's the direction?
How do we find? Okay.
How do we find the direction?
Okay. So we know that FE was going that way.
FE was going that way, so we wanted FB to go in that direction, right?
Yeah.
We wanted this force to go in that direction so it balances out.
Yeah.
So we know that FB is going in that direction. And we know that FB is equal to Q times V cross B.
Right.
So V cross B should give you FB. V cross B should point you in FB's direction.
Exactly. Hold on. Wait.
Right hand.
So.
V is going this direction, right?
So it's that.
B, right.
B.
V is going that direction.
Cross B.
Cross B, we don't know where B is.
We don't know.
We don't know yet.
Gives you up.
Gives you up.
The third one.
Gives you up.
So this one is somewhere here like this.
You're using left-handed.
Fuck. Hold on. Shit. Wait. Okay. This.
Right.
This.
B.
Oh, that's nice.
B.
And
Right. Gives you up.
okay. And that one is like where? Here. Okay.
Yeah, they're always perpendicular to each other.
Okay. Here.
B, B.
This way. This way.
Okay, so it should be inside the board, right?
Yep.
Inside. For it to work out. Yeah, I mean, there's two possibilities, inside or outside, because they always have to be perpendicular to each other, right? I mean, if something like this comes up, because it's going to be harder for you to to do it the opposite way around. It's really harder than when you have V and B, it's easier to determine F of B, right? Because
Yeah.
it's just Q, B. But when the other way around, yes, I know it's slightly harder. So there's always just two possibilities. Since it's always going to be perpendicular to these two. If this is in this way, the other one in this direction, the other one has to be either inside or outside. Try inside. If it gives you the right direction, you're right. If not, try outside. Gives you the right direction, the wrong direction, reverses. But yeah, in this case, V cross B gives you Q.
It does, right? Okay. Yeah. Like this. Okay. Yeah.
Cross
Yeah.
B
This inside and then up. Okay. Cool.
gives you F of B, which balances out the entire thing.
It will be so much fun on the exam when everyone will be doing something with their hands.
Yeah, I was sitting in class last time, and I just thought that when I checked one question came up, everyone was like, see, you have a problem like this, and if you just want to make it more complicated, you can just add a bunch of stuff to it. And people think it's more complicated when it's just not really anything else. I mean, you can say, don't ignore the mass. Oops, sorry. You can say, don't ignore the mass. If it gives you a mass, then you just add a new force, which is gravity, going in that direction.
Oh, and then you sum up
And you
Fe
sum-
plus F gravity equals.
You can sum up gravity.
Okay.
I mean, it's not a problem really. It's just adding more complications into the same problem, or just combining multiple problems into one. It's the same thing. I mean, if you know this concept, you know this concept, you know this concept, why don't you know all the concepts together? There's no reason not to.
Thanks.
Yeah, and the only other problem that I have this time is something we did really similar the other time is just a bunch of resistors. And we're way past that at this point. So, I mean, if you want, we can do it. If you want, we don't have to.
Okay.
It's kind of similar activity.
Do you have a lot of stuff like this?
I have them, but they're in Arabic. I mean, these I wrote myself, these three, but I have a bunch that are
Okay.
kind of similar to these. These are basically inspired from them.
Okay.
That are in Arabic. I'll translate them one by one. I do have to translate them because. Yeah.
Okay.
Okay then. PDF.
You're saving these?
Yeah. You want them?
Yes.
This is, I think, the first time that they ever came out neat. Yeah, let me email them to you.